The modern power grid is reaching its physical breaking point. As AI workloads surge, the infrastructure feeding them is fracturing under the sudden weight. A developer attempting to plug a new gigawatt-scale facility into the existing utility network today faces a 5 to 10-year wait in the interconnection queue. For hyperscalers locked in a race to deploy AI compute capacity, a decade-long wait for grid power represents an existential threat to their business models. To bypass this bottleneck, the industry is executing an aggressive pivot. They are building massive, autonomous behind-the-meter power plants directly on their data center campuses. Bypassing the grid does not eliminate the bottleneck. It trades utility delays for multi-billion-dollar construction and heavy industrial execution risks. This architecture is the islanded microgrid, a localized energy system designed to operate in total isolation from the regional power network. Severing the tie line forces the data center to balance its massive fluctuating compute loads using only the distributed energy resources located on site. Constructing independent power at this density requires the data center industry to operate at a scale and speed it has never attempted. Plugging into a regional grid offered relative predictability. Now, these companies are assuming the extreme financial fragility of procuring and building custom off-grid infrastructure. To accurately project the financial risks of this strategy, we must first look inside the physical engineering of these autonomous energy shells. The foundational building block of the off-grid data center is the modular power skid. These are heavy steel frames packed with critical hardware, pre-integrating uninterrupted power supplies, switchgear, and massive isolation transformers into a single deployable unit. Establishing true autonomy requires a specific technological leap: grid-forming, or GFM, inverters. Standard grid-following inverters are passive, synchronizing to an existing utility signal. Grid-forming inverters do the heavy lifting themselves. They act as a controlled voltage source, autonomously generating the continuous sine wave that dictates the microgrid's voltage and frequency. To maintain stability during intense, unbalanced phase loads, these inverters are tightly integrated with high-capacity battery energy storage systems that actively smooth the electrical output. This system still needs a primary source to generate the actual electrons. Because 24/7 AI compute requires highly dispatchable baseload power, intermittent renewables are insufficient. As a result, hyperscalers are replacing standard diesel backups with heavy-duty aeroderivative natural gas turbines and solid oxide fuel cells. The capital flowing into this specific hardware is massive. Between late 2025 and early 2026, over $7.6 billion was committed to fuel cell technology to act as prime power for AI workloads. Combining custom skids, grid-forming controls, and heavy gas turbines transforms a data center project into a complex, heavy industrial engineering megaproject. A persistent belief among developers suggests that building autonomous power at the gigawatt scale is entirely uncharted territory. The architectural DNA for these systems was already tested and perfected over the last decade by heavy industrial operating in the world's most isolated environments. The true historical baselines for these data center microgrids are the remote liquefied natural gas plants and isolated Australian mining operations. The scales line up perfectly. Islanded power shells built for those heavy industrial sites consistently range between 376 and 600 megawatts, matching the 50 megawatt to 1 gigawatt profile required by modern AI facilities. The hardware lists match. Booth models rely on fleets of aeroderivative gas turbines, heavy switchgear, and massive battery energy storage systems. The integration complexity, the control algorithms needed to balance the load, and the extreme operating parameters mirror each other closely across both sectors. Because many of these remote industrial sites received government co-funding, they were required to publish rich, empirical data on their construction and operational timelines. Investors sizing up the AI infrastructure build-out do not have to guess about execution risks. They can analyze the exact failure points that delayed these identical industrial power islands in the past. Deploying this heavy industrial hardware today means attempting unprecedented speeds of construction while navigating severe global supply chain bottlenecks. The physical constraints are severe. Lead times for large power transformers have hit 128 weeks, and contractors face acute shortages of specialized labor. The fragility of this execution is visible in the recent CoreWeave data center project in Denton, Texas. A combination of weather disruptions and minor design revisions triggered a 60-day delay at the 260-megawatt facility. The financial fallout from that 2-month slip was immediate. It caused a massive cut to revenue guidance and wiped out $14 billion in market cap value. The underlying mathematics of the AI boom are brutal. Deferring AI compute revenue currently costs operators roughly $833 million per gigawatt every single month. What happened in Denton is a predictable symptom of low standardization builds, verifiable through live tracking data. This chart displays confirmed versus expected project delays across major data center power buildouts, tracked by Occam Edge. In the lower tiers, projects that scored low on design standardization have already accumulated 6 to 7 months of confirmed delays. High standardization projects show a different outcome. These builds show 0 confirmed delays and track exactly to their expected delivery schedules. With an islanded gigawatt, any hardware delay represents an existential threat to infrastructure viability. How can developers and lenders systematically identify these multi-billion-dollar traps before they deploy capital? The answer lies in a proprietary standardization score derived from the evidence of the historical industrial microgrids. Project health is evaluated across 5 critical risk dimensions: design reuse, modular assembly, permitting pre-certification, diverse procurement, and strict interface standardization. Developers cutting corners on these metrics predictably fall into the same 6 to 7 month delay cycles that hindered earlier industrial megaprojects. Enforcing rigorous, repeatable design and strict interface discipline are the only proven methods to ensure off-grid AI infrastructure remains bankable. For any stakeholder considering grid defection, the required next step is pressure testing whether the assumed time savings will actually materialize. Once you factor in the multi-month lead times for custom procurement and heavy engineering, the actual speed advantage of going off-grid versus optimizing a utility connection is much narrower than the industry assumes. Surviving this deployment phase requires a continuous, real-time assessment of site-specific variables, from local permitting hurdles to granular supply chain bottlenecks. By applying probabilistic risk analysis and matching new architectures against historical industrial DNA, operators can translate early engineering inputs into accurate schedule forecasts. A single miscalculated delay now destroys billions in enterprise value. Traditional financial models that ignore physical hardware constraints cannot see these failures coming. The defining question for the industry is not whether to build on-grid or off-grid. It is determining which pathway delivers functional capacity fastest at the lowest risk. The winners of the AI infrastructure race will be the ones who leverage historical project intelligence to secure their timelines long before the first transformer is ever ordered.